All right, let's just jump right in. For pretty much the last half century, everything, all our tech progress, has been built on one thing, the silicon chip. But here's the thing, that foundation, it's starting to show some serious cracks. So today, we're going to talk about what's next. And it's a huge shift. We're talking about computers powered not by electricity, but by pure light.
And look, this isn't just some dramatic headline. It's the cold, hard reality for engineers and scientists all over the world. You've heard of Moore's Law, right? That famous prediction from back in 1965? It's been the engine driving our entire digital world. But that engine, it's really starting to sputter. Why? Because we're shrinking transistors down so small, we're literally at the atomic scale now. And at that level, the basic laws of physics are basically putting up a giant stop sign. So you gotta ask, if the very idea that gave us everything, from the phone in your pocket to the entire internet, is hitting a wall, what's gonna carry us into the future?
Okay, so before we can really get into the solution, we've got to understand the problem, right? Let's break down exactly what's going on with our good old electronic computer chips. It basically comes down to three major roadblocks, three walls that silicon is just slamming right into. You've got the heat wall, the speed wall, and the quantum wall. And that last one is where things get super weird. I mean, components are so tiny now that electrons just start misbehaving. They literally tunnel right through physical walls they shouldn't be able to cross. That causes all sorts of errors. It's the ultimate quantum dead end. So first up, the heat wall. It's actually pretty simple. Every single time an electron zips through a wire, it creates a little bit of heat. It's just resistance. Now imagine that happening in billions of transistors, all crammed into a space smaller than your thumbnail. The heat just skyrockets. It gets so intense that we literally can't pack things any tighter or run them any faster without the risk of them, well, melting. For places like data centers, this is an absolute nightmare. And then there's the speed wall. And this one is kind of ironic, really. The transistors, they're insanely fast. They can switch on and off at unbelievable speeds. But the problem is the tiny little copper wires that connect them all, the interconnects, they just can't keep up. It's become the single biggest bottleneck holding back performance. It's like having a city full of supercars that are all stuck in a massive traffic jam. The data just can't get where it needs to go fast enough. Okay, so if electrons and the copper wires they move through are the big problems, what if we just got rid of them? What if we could replace them entirely? And that right there is where light comes into the picture. We're going to see how it can help us build a completely new kind of computer. This is the whole idea behind something called photonic computing. And the concept is, at its heart, really simple, but also kind of mind-blowing. Instead of pushing electrons around to represent ones and zeros, we're going to use photons, the actual particles that make up light. It's a fundamental shift from electronics to optics. And this is where you can see why this is such a big deal. Just look at the basic physics. Electrons have a charge, right? So they bump into each other, they repel each other, they create all that heat we talked about. Photons, they're neutral. They couldn't care less about each other. They can literally pass right through one another without any interaction at all. That means no resistance, no heat from just moving around, and oh yeah, they move at the speed of light. This is it. This is the fundamental reason everyone's so excited. All right, so we know photons have these incredible, almost magical properties. But what does that actually translate to when you're trying to build a computer? Well, let's take a look at the superpowers of light. The first big one is bandwidth. And we're talking about a capacity to carry information that is, for all practical purposes, infinite. It's just staggering. The real trick, though, is figuring out how to tap into all that potential. And the key to unlocking it is this really cool technology called wavelength division multiplexing. You can just call it WDM. It's a clever way to send tons of different data streams down a single fiber optic cable, just by putting each stream on a different wavelength, or basically a different color of light. And this is the perfect way to think about it. Imagine you have a single, slow country road. WGM is like transforming that road into a massive, multi-lane superhighway. But here's the cool part. Every color of car gets its own personal, dedicated lane. So a red car never bumps into a blue car. They're all moving at max speed with zero traffic jams and absolutely no interference. The amount of data you can move is just astronomical. So let's just recap the big picture here. When you put all this together, what do you get? You get crazy speed. You get that massive bandwidth we just talked about. You get zero heat when you're moving data around. You get total immunity to electromagnetic interference, all that electrical noise, and you even get better security. I mean, these are truly game-changing advantages that tackle silicon's biggest weaknesses head-on. Now, of course, if it was that easy, we'd all have photonic computers sitting on our desks right now. The reality is, it's not that simple. There are still some really significant engineering challenges we need to figure out before this technology can really take over. You can really think of them as three big hurdles to clear. The first one is conversion. Switching signals from electricity to light and then back again, it's still not perfectly efficient. It costs energy, and it takes a little bit of time. Second, we don't really have a great way to store information with light yet. A practical version of optical RAM. And the third one, this is kind of the holy grail. Building a true all-optical transistor. A switch made of light that can be flipped by another beam of light. That's the real key to unlocking pure optical computing. And then there's a more down-to-earth problem. A lot of these tiny, delicate optical parts are super sensitive to temperature. I mean, even a tiny change can throw the whole system out of whack. So they need these active stabilization systems to keep everything just right. And that, of course, adds more complexity and uses more power. So, where does all of this leave us? Well, it brings us to what's probably the most realistic and, honestly, the most exciting path forward. We're not talking about an all-optical world tomorrow. Instead, we're looking at the beginning of a hybrid age. And this is probably the most important thing to remember from this whole discussion. The future isn't about replacement, it's about augmentation. For the foreseeable future, photonics isn't going to just replace electronics, it's going to work with them. The two are going to become partners, with each one playing to its own unique strengths. And this really shows you how that partnership works. Electronics will keep doing what it's amazing at, the general thinking, the control systems, storing memory. Meanwhile, photonics will come in and handle the really heavy lifting. Things like moving insane amounts of data at lightning speed and supercharging all those parallel computing tasks that are so crucial for things like AI. And this isn't just theory. We're already seeing this hybrid approach making huge waves out in the real world. The number one place it's having an impact is inside data centers, finally solving that data traffic jam we talked about. But it's also completely changing the game for AI hardware, for high-performance supercomputing, and it's even giving us a better foundation to build the quantum computers of the future. So let's end with this thought. The silicon chip gave us the information age. It totally reshaped our world. Now, as we're learning to actually compute with light itself, the big question isn't if it's going to change the world again. The question is how. What kind of new age are we on the brink of creating?